to Welcome to this video. Today I will be talking about the primal and the dual problem. So in the previous video I talked about cones which are useful in conic programming, k and k star, and I also said something about k star star. So we have these different cones. So this is a closed convex cone, and this is also a closed convex cone, and this is also a closed convex cone, and this is equal to k. And the idea is now to frame the dual problem. So what is the primal problem first? From the primal problem we will slowly build towards the dual problem. So one thing to remember in the discussion is the fact that k star is defined as set of all v belonging to v, which can be identified with v star also. So I put a star here for now, such that I erase this, such that what we have is v u greater than 0 for all u belonging to k. And now this is the dual cone. So this is called the dual cone, and this cone actually contains the separating hyperplane that separates the set k. So this is important. So it is easy to see that suppose I have some x not belonging to k, that is a part of but it belongs to the vector space v, then there exists a hyperplane q such that the inner product of q and x, it is less than 0, but q with u is greater than equal to 0 for all u, let's write u here, for all u belonging to v. So for all u belonging to k. So this is the definition of the separating hyperplane. So this is separating hyperplane theorem, and you can see this definition here, particularly this is exactly same definition that appears here. So basically what I can say is q is an element of k star. So this is a general feature that the separating hyperplanes are the elements of the dual. So this will be useful later on. So with this let's write the primal problem. So the primal problem is a optimization problem written as infimum over ax such that I have a linear map acting on x giving me y. So this is a linear map, and x belongs to some convex cone. So this infimum I can sometimes replace with minimum also, and we are not going to bother about the subtleties in doing the thing. But this is the primal problem. It is an optimization problem, and one can show that this primal problem can be written in a more general way as infimum over some a tilde x tilde such that x tilde belongs to S, some set. So this is a more general way, in the sense this S is just a convex set, but here this k is a closed convex cone, and this lambda is a linear map. So lambda goes from v to v prime linearly. And now with this we have the primal problem, and let's define the primal feasible set also. So this is a set G defined as x belonging to v such that lambda of x is y and x belongs to k. So this is called the primal feasible set. Primal feasible set. The point is that the optimal values, which is the primal value that this optimization will take, it will take within this primal feasible set. And with this we can define the Lagrangian now. Let's define the Lagrangian. Lagrangian. So let's define the Lagrangian of this optimization. It's an optimization. So L as a function of x and qz. So q and z are Lagrange multipliers, which will give penalties to the constraint basically. So I have ax minus z with lambda x minus y and minus q with x. So let's see what this means is that this is giving a Lagrange multiplier to the equality constraint. So this is the equality constraint, and this is giving a Lagrange multiplier to the fact that x should belong to k, and this is equal to 0. Now what we can say is that now we can say some important points about this Lagrangian basically. So what we can say is supremum over z and q. So I have the Lagrange multipliers. If I take the supremum over this of the Lagrangian is equal to, so this is equal to two things. It will either be equal to infinity whenever x does not belong to G, or it will be equal to ax when x belongs to G. So now how can one see this? So it's very simple to see. So let's first look at this constraint. So whenever x does not belong to G, it means that either x does not belong to K, or lambda of x minus y is not equal to 0. So these are the two possible ways. And if this happens, then I can find a separating hyperplane Q such that Q times x is always less than 0. This I can find. And the point is, now I can rescale Q and use this to drive the entire expression to infinity. So this is important. So this gives us the infinity here. Similarly, if I have this not equal to 0, then I can appropriately choose z, lambda x minus y, such that this quantity is less than 0. This is because this quantity will either be positive or negative, and based on the sign I can choose z to be minus z or plus z, and then I can rescale the z again to get infinity. So this means that outside the set, this supremum takes an infinite value. You can think about it as giving a penalty for not belonging to the set. And inside the set, it will take ax, because inside the set this is equal to 0 and this is positive because this is the separating hyperplane. So this makes sense. Now what we do is we write the primal problem in a different fashion. So primal problem is, it is simply ax optimization. So infimizing over x the supremum of zq, and then I have the Lagrangian x q z. So this is the way to frame the primal problem. And here what I have done is I have lifted the restriction of x belonging to G by using the fact that this supremum will give the penalty appropriately. So this is something. And now I talk about the dual problem. The dual problem is nothing but interchanging the supremum and infimum. So the dual problem is supremum and then infimum of L, X, Q and Z. So the supremum is over Z and Q and the infimum is over X. So now observe that the dual problem is always less than equal to supremum, infimum over, instead of x belonging to V, I can say x belongs to G, L of x, Q, Z. So because there is a infimum and I am restricting the set to G, so G, because of that there is a greater than equal to this sign, and this is again greater than equal to I mean this is upper bounded by I can remove the supremum now because x is already in G, and this gives me infimum over x belonging to G Ax, which is P. So this means that the dual problem is always lower bounded by the upper bounded by the primal problem. So what it means is that D is always less than equal to the primal problem. And this is called weak duality. This is called weak duality, and now we will talk about the dual problem. So let's talk about the dual problem now. So for talking about the dual problem, I will use this expression here. And what I will do is I will say that let G of QZ be equal to infimum over x belonging to V, L of x, Q and Z. Let G be this, and then the dual problem will be defined appropriately, but here we can do some simplification actually. So this can be written as infimum over x belonging to V times zy. So what I am doing is I am separating the Lagrangian into parts which give rise to the Lagrange multiplier from the equality constraint and the other constraint of the x belonging to the set K. So this can be written as this plus a minus lambda star z minus q and x. So this is you can check that this is the Lagrangian, so this is equal, and lambda star I have to define appropriately. So z instead of a it will be lambda of x is equal to lambda star z x. So this is the unique map that satisfies this constraint. So this is the adjoint of the linear map, you can say. So this is the adjoint. And now what we have is we have this infimization problem, and you can call this as a vector omega. And now if omega is equal to 0, then this infimum over x belonging to V does not appear because there is no x and we have the value zy. If omega is not equal to 0, then I can appropriately find x, that is minus omega, and rescale it to minus infinity basically. So this is basically G. So let me write it down. So G of Q Z is equal to zy for omega equal to 0 and minus infinity for omega not equal to 0. And now what we need is the supremum value. We can say that supremum of, so here if you remember the dual problem had a supremum here, so it will be supremum of zy subjected to the constraint that omega is equal to 0, because otherwise it's minus infinity if it's not 0. So omega equal to 0 is the condition that a minus lambda star z equal to q, which belongs to k star, the separating hyperplane. So this means it is subjected to the condition that a minus lambda star of z belongs to k star. And then the second point is that what z belongs to v prime star. So v prime lambda is a map from v to v prime. So z here is the in the output space. Otherwise lambda star of z will not anyway make sense. So with this idea we have the dual problem, which is again an optimization problem. So this is the dual problem, and it is kind of obtained from the primal problem. So let me write it down in the summary. So the idea is you have the primal problem, and instead of infimum I am now writing maximum and minimum. So you have minimum over ax such that lambda of x is equal to some constraint. So let me see. So what was the constraint? So let's suppose the constraint is b and x belongs to k. Then the dual problem is maximization of y with respect to b. So here b was actually y, so it's a bit difficult notation, but let's stick to the previous notation. So lambda x equal to y, x belongs to k, and here it will be z and y such that a minus lambda star z belongs to k star and z belongs to nu prime, and lambda is a map from nu to nu prime. So this is the primal and the dual problem. These are the two optimization problems which are very closely related, and in the next video we will talk about robustness as a semi-definite program. So the main idea here is to observe that the primal problem has a value p, the dual problem has a value d, and d is always less than equal to p. And the important point is that for our discussion we will assume that p is equal to d. So this comes from weak duality, but we will take something called as strong duality. So in strong duality we will assume that p is equal to d. So that's it for this video. Thank you.